Okay. We're going to keep talking about the Tutte polynomial. So today I'm going to say something about its coefficients. We know it's a polynomial in x and y. We're going to talk about its coefficients. And if you want to read about this, it's in Neil White's book, Matroid Applications. Pages 235 to 240, more or less. And then I'm also going to talk about this article of mine called the Catalan Matrice. Which is in the Journal of Combinatorial Theory, Series A, but you can also just get it from my website if you're interested. So what's the idea of what I want to say today? The idea is that we have, so far we have basically two ways of thinking about the Tutte polynomial. Okay? Now, if you look at the recursive way of thinking about it, where the Tutte polynomial in x and y is the deletion, is the Tutte polynomial is the deletion plus the contraction for when you don't have a co-loop or a loop. If you have a co-loop, you multiply by x. And if you have a loop, you multiply by y. And t of the empty matroid is 1. So from these properties, we're going to see that the Tutte polynomial always has positive integer coefficients. Because all you're doing is multiplying by x, multiplying by y, and adding things. You never subtract anything. You never divide by anything. So the Tutte polynomial has non-negative integer coefficients. Okay. And one of the common things that you see often in combinatorics, whenever a combinatorialist finds a number, and this number is a non-negative integer, then a combinatorialist will say, oh, that means it's counting something. Okay? So if the coefficient of x cubed y to the fourth is 7, then what does that 7 mean? It's a positive integer. So what is the counting problem whose answer is 7? Okay? What do these coefficients mean? That's the point of today. The coefficients of the Tutte polynomial. So this is an abbreviation, coefficients. For example, this guy that we keep talking about, we saw that its Tutte polynomial looks like this. And so all the coefficients are non-negative integers, and the question is, why is it that some of these are 1s, some of these are 0s? What is the property that makes certain coefficients equal to whatever? Now, remember that if you plug in 1, 1, we saw what happens. We saw that you get the number of bases. We proved that, and if you look at what happens when you plug in 1, 1 here, you're going to see that it's the sum of the coefficients. Sum of the coefficients. And so if you want to pick out a certain coefficient, all the coefficients add up to the number of bases. And so what we're going to try to do is say, well, this coefficient is the number of bases that satisfy something. That's basically what we're after. So we want to say that the coefficient of x to the I, y to the j, is the number of bases such that blah, 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 blah. Something involving I and j. That's what we're after today. Okay? And so this is how we're going to do it. Say that M is a matroid, And you're going to take the ground set and you're going to order it in some way. Order the elements of the ground set in any way that you want, but it's a linear order. You say one is first, the other one is second, and so on.
You just want to identify them with
what you want is,
one.
Yeah, sure. You just identify them with the numbers 1 up to n in some order. And you're free to choose the order. And now I'm going to make some definitions. Let's say that you take a basis of the matroid. Okay. So definition. An element E, which is not in the basis, is, we're going to call it externally active. If the following holds. We have a basis B, okay, and we have an element which is not in the basis. So we said that if you have a basis and you have an element not in the basis, then when you add E to the basis, you're going to create a unique circuit. So you're going to look at that circuit, which contains E and some of the things in B, and you're going to figure out if E is the smallest guy in that circuit. E is the smallest in the circuit, which we call the basic circuit C of B, comma, E. Okay, that's what you're going to do. And the reason I need to order the ground state is so that I can say what it means for an element to be the smallest one. I mean the smallest in that label. Okay? And so let me do an example. Let's say that we are in the matroid of this graph. Okay? And the first thing I have to do is I'm supposed to order the ground set in any way. In other words, I'm supposed to number the elements in whatever way I want. And so let me just order them like this: 1, 2, 3, and 4. Okay. So then I'm going to make a list of the bases. So the bases of this guy are 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4. Okay. And I want to figure out which elements are externally active for each one of these bases. So for example, let's look at 1, 4. Okay, so the basis 1, 4 has 2 elements outside of it, 2 and 3, and we want to determine whether each one of them is or is not externally active. So for example, 2 is 2 externally active. Well, you're going to look at 1, 4, and joining 2. And the circuit that you form is 1, 2, 4. And the smallest guy is not 2. So in other words, so you add 2, but 2 is not the smallest guy in the circuit, so 2 is not externally active. When you add 3 to 1 and 4, what is the circuit that you form? You have 1, 3, and 4, so the circuit that you form is 3 and 4, and the smallest guy there is 3. So this guy is externally active. Okay. So that's what you do. And you get that 3 is externally active and 2 is not. Okay. For 1 and 2, if you add 3, 3 is not the smallest guy in the cycle 1, 2, 3. 4 is not the smallest guy in the cycle 1, 2, 4. So there's nothing. For 1 and 3, you can see that there's nothing. For example, for 2 and 3, you'll see that when you add 1, the cycle is 1, 2, 3, and 1 is the smallest guy there. But 4 is not externally active. And for 2 and 4, you're going to see that if you add 1, 1 is minimum in 1, 2, and 4. And if you add 3, 3 is minimum in 3 and 4. So 1 and 3 are externally active.
I'm sorry, what was the what?
why is 4 not externally active and 1, 3? Because when you take 1, 3, and you add 4, then the cycle that you form is 3 and 4, and the smallest guy in that cycle is 3. It's not 4, which is the one that you add.
I got it. Yeah.
So that's what you do, and this probably seems kind of strange and arbitrary to you, but that is the definition. Okay. And you saw that I left an opening here, because I'm going to define another thing. Now I'm going to define something called internally active. So I'm going to say an element inside the basis is internally active. What is this going to mean? Well, I wanted an extra spot here. And I also want to draw the dual. What does the dual graph look like here? The dual graph looks like this. You get a vertex here, a vertex here, a vertex here, and they get joined like this. This, like this, and like this. Okay. And what are the labels? Well, this is 4, this is 3, this is 1, and this is 2. So the dual guy looks like this. That's the dual. What are the bases of this guy? Well, we know what the bases of the dual are. They're just the complements of the basis of the matrix. So 1, 2 goes to 3, 4. 1, 3 goes to 2, 4. 1, 4 goes to 2, 3. 2, 3 goes to 1, 4. And 2, 4 goes to 1, 3. Now, I'm trying to decide if an element I in the basis is internally active. Well, if my element I is in the basis, then it's not in the complement of the basis. And so I'm going to say that I is internally active here if it's externally active here. In other words, if I is the smallest in the basic circuit, but now the basic circuit for the dual. So instead of B, I have B star, comma, I. In other words, it is externally active for the dual basis. Okay? So again, let's do that here. Um, 3 and 4. So what can be internally active? Well, inside 1 and 2, the guys that can be internally active are 1 and 2. When you add 1 to 3, 4, 1 is the smallest guy in the circuit. And if you add 2, 2 is the smallest guy in the circuit. So 1 and 2 are internally active. For 1 and 3, it looks like 2 is not. And 4. Oh, sorry. So for 1 and 3, we need to go to 2, 4. And now it looks like 1 is internally active and 3 is not. For 1 and 4, you go to the basis 2, 3, and you find that 1 is internally active and 4 is not. For 1 and 4, you go to 2 and 3. So, sorry, for 2 and 3, you go to 1 and 4, and you find that neither is internally active. And for 2 and 4, you go to 1 and 3 here, and you find that neither is internally active. Okay. So, yeah.
So, minor observation, but it's no accident here that the smallest elements got mapped to the biggest element. And up to labeling.
So your question is basically that.
So
You mean going from here to here?
From the
From the matroid to its dual? I see. So what you're telling me is basically that these two guys are isomorphic, and the isomorphism says send 1 to 4, send 2 to 3, and so on. That actually is an accident. And it's only one reason why you can see that it's an accident is that this guy happens to be self-dual. But that's generally not going to happen. And so that's not something that always happens. Okay. So theorem. The coefficient of x to the I, y to the j is equal to the number of bases that have I internally active elements and j externally active elements. Okay. In other words, I didn't want to erase that. In other words, the top polynomial of a matroid is equal to the summation over all the bases of x to the number of internally active elements, y to the number of externally active elements. So that's my theorem. Not my theorem, that's Krapo's theorem. So that's exactly what we wanted. It tells you exactly what the coefficient of x to the I, y to the j means. The number of bases that have this property.
Okay. So we have the.
So this is independent of order.
And that's the amazing thing about this is that these definitions depend on an ordering of the ground set. And there is absolutely no reason to believe that if you change the ordering, you should get the same numbers. Absolutely not clear. And well, this is a proof, right? But this is absolutely not clear. And actually, this is something that still to this day, there's proofs, but I don't think there's really a very nice explanation for why these quantities don't depend on ordering.
For a given basis, it will depend on order, though, right?
Because that's the thing. For a given basis, it totally depends on the order.
But when you get the
so somehow when you change the numbering, it turns out that the bases that had 3 internally active elements and 1 externally active element, all of a sudden became some other basis, and maybe that other basis became this one. The bases just get jumbled around, so that these terms get jumbled around, but somehow when you add them up, you get the same answer. That's still a little bit mysterious. Of course, it's proved, because this is a proof. But it's still a little bit mysterious why that actually is true. Okay. So for example, what does this say? What this says is that we can compute this thought polynomial just by looking at this table. The thought polynomial of the matroid is, you take x to the number of guys here, y to the number of guys here. So you get x squared plus x plus xy plus y plus y squared. And that's the top polynomial of this matrix. And so this gives you yet another way of computing top polynomials by picking and ordering, drawing this table, and computing this. Okay? Now, the reason that I didn't want to erase this is because I want you to compare this and that. Because that matroid and this matroid are very closely related to each other. If I number these guys in the same way, 1, 2, 3, 4, and then I number these guys 5 and 6, then that matroid is obtained from this one by deleting a loop and deleting a co-loop. Or in other words, let's go backwards. If you start with that matroid, you can get this one by adding a co-loop, adding a loop. But what does that do to the top polynomial? You add the co-loop, it multiplies it by x. You add the loop, it multiplies it by y. And so therefore, if you take that polynomial and multiply it by x, y, you should get this one. Which you do. Right? X squared times xy is this one, x times xy is this one, and so on. Okay. This one we had computed using that tree of computation. And now we have an alternative way of computing it.
In terms of how it's going to change your chart, it's going to put a 5 in all of the bases. Is that right?
In terms of how
Like,
it changes the chart to go from this matroid to that matroid.
right.
I guess it puts a 5 in each one of the bases,
And it puts a 6.
and it puts a 6 in each one of the complements. And presumably what happens is that these guys all have a 5, and these guys all have a 6. That is what happens.
Yeah.
But this is nice, and actually you should try doing this for different matroids and for different labelings of the same matroid, and you'll see that it's really kind of amazing that this works out and that it doesn't depend on the label. Let me give you a sketch of the proof of why this is true. Actually, I'm supposed to use this stuff. Because the proof is also really nice, actually. So, sketch of the proof. There's basically two observations that we're going to make. The first observation says this. For each basis, consider this interval. So for each basis, you're going to delete the internally active elements, and then you get some set. And then you're going to add the externally active elements, and you get some other set. Okay? And of course, this set contains this set. And so therefore, if I look at the Boolean lattice of all possible sets, this guy is above this guy, and this is an interval in that poset. Okay? So let's do that for these guys. So what is the interval? For the basis 1, 2, you delete the internally active elements, so that gives you the empty set. And you add the externally active elements, there's nothing to add, so you get 1, 2. And that's some interval over there. For 1 and 3, you start by deleting the internally active elements, so that gives you 3. And then you add the externally active elements, you didn't add anything, so you get this guy. Okay? And that gives you some interval over there. Then for 1, 4, you delete the internally active elements, so you're left with 4. And you add the externally active elements, so you get 1, 3, 4. Okay. For the next one, you delete nothing, so you delete nothing from 2, 3. And then you add the 1. And for this one, you delete nothing, and then you add 1, 2, 3. You add everything, and you get 1, 2, 3, 4. Okay, so each one of these bases is going to give you some interval in this poset. And now let me go ahead and draw those intervals. So the interval from 0 to 1, 2 looks like this. one interval. The interval from 3 to 1, 3 is just this segment. Then the interval from 4 to 1, 3, 4. So where's that? From 4 to 1, 3, 4, you go through 1, 4 and 3, 4. Okay. Then the interval from 2, 3 to 1, 2, 3 starts here and ends here, and it's just a straight line like this. And finally, the interval from 2, 4 to 1, 2, 3, 4 goes through this guy and this guy. And you notice an amazing property here, which is that what I just did covers the whole poset exactly. Nothing is left outside. Everything is covered and there's no overlap. So that's the first really nice fact about these definitions, is that when you do this, these intervals exactly cover the Boolean lattice to the n. Which is, I think, really nice. And again, you'll see that if you relabel, then the covering changes. But it's always a covering. Okay.
And that's also, that was independent of what the matroid was.
And this is going to work for any matroid.
So it's just the Boolean lattice on the ground set.
Right. So for any matroid, you get a covering of the Boolean lattice on the ground set. So that's the first step of the proof. Okay. In other words, each set in the lattice can be written in a unique way as you take a basis, you delete some internally active elements, and you add some externally active elements. Unique. This is a restatement of this. Any subset of 1 to n can be written uniquely as a basis minus some internally active elements plus some externally active elements. Okay? That's the first observation. And the second observation is that, I mean, what's the idea? Where are we trying to get here? The idea is that now I want to look at the top polynomial, right? The top polynomial is given by the summation over all subsets of my ground set of something. Now, I found a way of writing each S in this summation as B minus I union E. And I plan to substitute that here. S equals B minus I union E. And to substitute, I need to get rid of the occurrences of S. But now, what's the size of S? Well, that's number of elements of B minus number of elements of I plus number of elements of E. And so the only tricky thing is, what is the rank of S? Does it only depend on B, I, and E? Well, that's not clear at all, but it turns out that the rank of this guy in the decomposition does depend only on B, I, and E, and in fact it's just the rank of the matroid minus I. So effectively what this does is that you start with a basis. When you delete the elements of I, you drop rank I times. And when you add the elements of E, that doesn't add rank at all. That is what turns out to happen in this decomposition. Okay? And so therefore, I can substitute here R minus the rank of I. The rank of S is R minus the rank of I. And then Y minus 1 to the. What's the size of S? Is rank minus size of I plus size of E. That's the size of my set S. Minus the rank of R minus I. That's what I get by rewriting each S in this way. So now I get summation of x minus 1 to the R minus I is just I. And Y minus 1 to the R minus I cancels R minus I, and I just get E. And now what happens is, well, if I now consider the terms that have a particular b in here, then how many times am I going to obtain x minus 1 to the I, y minus 1 to the j? Well, what you have to do is, out of the internally active elements, choose I of them. And out of the externally active elements, choose j of them. I'm doing this a little bit fast, but you basically sum from I equals 0 to I of b, sum from j equals 0 to E of b. You get this. And now what you see is that this summation of I of b choose I, x minus 1 to the I, is a binomial summation. So it's 1 plus x minus 1 to the I of b. And this summation of these guys is another binomial summation, which gives you 1 plus y minus 1 to the E of b. Which is what we want, a summation over the basis of x to the internal activity, y to the external activity. Okay. And so, of course, there are some things for you guys to check. You should check that this actually works out. But the point is that this is just a computation that you can work out. The key properties are these two. This is really the essence of the theorem, and this is really where you have to do some matroid theory and prove that these two things are true. If you want to read this, it appears in this book that I listed over there, in Neil White's book on matroid applications. So that's that. I don't know if any of you guys have some experience with Grosvenor basis theory, but in Grosvenor basis theory, the same thing happens, that you pick an ordering, and then in the end, the ordering doesn't matter. And a lot of people have wondered if this is Grosvenor basis theory in disguise, and really that's the explanation for this theorem, is that no matter what initial order you pick on the monomials, you get some bigraded Hilbert series that is independent of the ordering. And that's really kind of a nice open question that no one really knows how to answer. That's what I mean when I say that it's not so clear why this doesn't depend on the ordering, and it would be nice to have a nice conceptual explanation for that. Okay. Let me give you an example of this. A matroid with a very nice top polynomial. We've seen that top polynomials are complicated, and I'm going to show you a matroid that has, I think, maybe the nicest top polynomial that we know. Because there are not a lot of matroids whose top polynomial we know. In fact, so far we computed top polynomials for uniform matroids and uniform matroids and uniform matroids. That's all we know. And really the reason is that it is hard to find top polynomials of nice infinite families. I told you guys, for example, in my thesis I did this for some nice matrix of root systems, which you can do it there, but this is really a difficult question in general. If I give you a matroid, a big matroid, or a family, an infinite family of matroids, what's the top polynomial? It's not easy. It's not easy, and usually you just don't get a nice answer. But there's a matroid where you get a very nice answer, which is the Catalan matroid. You guys know the Catalan matroid very well because it is the matroid of problem set 1. It's the matroid of Dyck paths. So what are the bases of this guy? We said that they are Dyck paths, right? So it's some path that looks like this. It takes steps up, steps down. And it never crosses the x-axis. And it starts at 0, and it ends at 2n. In other words, it takes exactly n steps up, n steps down. Okay. What is the basis here? Well, we said let me write both the basis and the complement of the basis. So the basis is the up steps, right? 1, 2, 3, then you go down, so 4, then you go up 5, then you go down at 6, 7, and 8, then you go up 9, then down 10, then up 11, 12, down 13, up 14, and down 15, and 16. This is a typical basis of the Catalan matroid, and this is a typical basis of the dual. Okay. So these are the bases. Now, if we want to carry out this program of using Krappos theorem to compute top polynomials, the first thing we're going to have to do is pick an ordering on our ground set. But here we are lucky because actually the ground set already comes with a very natural order. 1, 2, 3 from left to right. So the ground set comes with a nice order right away. And so now what I want to do is for each basis, I need to describe to you what are the internally active elements and what are the externally active elements. There's no reason to think that might be possible or it might be nice, but it turns out to be very nice here. So if B is a basis, then I'll tell you what the internally active elements are. Well, here, in this example, they are 1, 2, and 3. That's it. 1, 2, and 3. And in general, the internally active elements are just the first string of up steps. That's it. So the internally active elements are all the up steps that you take before the first down step.
Question.
Yeah?
Can you tell me what a circuit looks like? So like
That's the question, right?
right. So if for the externally active, because at least that's well, no, it doesn't matter. So 1, 2, and 3 are externally active for B star.
Mm-hmm.
So it says if you add 1, 1, 4 is a circuit because it's an up down. Is that true?
So Kim's question is this: How can you prove something like this if I defined internal activity in terms of circuits, but we don't really know the circuits of this guy? Well, you figure them out. So that's what you do. Is the first step in proving this theorem is saying, okay, well, I know what the bases are. Now I need to describe what the circuits are. And so there's a lemma that says a circuit is something. And so, I mean, the point being that to prove all of this, you need to understand this Catalan matroid C sub n. So we know the basis, but we would like to understand the circuits if we want to prove theorems about this. We want to understand everything. I mean, and this is all in this paper that I wrote, the Catalan matroid. This is a description of the circuits, the independent sets, the spanning sets, the flats, everything. But of course, if you want to prove theorems about this matroid, you have to understand this matroid. And so there is some preliminary work. But once you've done that, and you know that this is true, then you can prove it. Okay? And I don't really have time to show you any of this, but this is what happens, and this is the reason that we can understand this matroid well.
Federico, you just work. You would like work with the definitions of a circuit and with the what you know about the matroid, and then you would be able to figure out what the circuits what they would look like.
Yeah. So that.
Work with the definitions.
Exactly. So let me give you an example. These are the bases, right? So let's say you want to figure out what the spanning sets are. We know that a spanning set is something that contains a basis. So what you do is you take a basis and then you add up steps. So if you take a basis and you add up steps, what that means is you're never going to go below the x-axis still. You just might get higher. And so one thing you can prove is that the spanning sets are exactly the paths that never cross the x-axis, and they might not return here. They might go higher. And so this is the kind of thing that you do. You say, okay, what's a circuit? Well, a circuit is something that we know how to describe circuits in terms of bases. We know what the bases are, and so then you can describe the circuits. And this is the kind of thing that you do. And you can describe all of these things combinatorially in terms of paths. Okay? And once you've done that, you show this. What's the next thing that you show? What are the externally active elements? Well, it turns out that they're just this one, and this one, and this one. So they turn out to be exactly the points where you bounce on the x-axis. So in this case, they are 8, 10, and 16. And in general, they are the down steps where you bounce on the x-axis. And in general, this is true for any basis. And so therefore, we have a theorem. And the theorem basically says that the Tutte polynomial of the Catalan matroid is given by the summation over P is a Dyck path. And then you just do I of P, E of P, where I of P is the number of up steps before the first down step, and E of P is the number of bounces. On the x-axis. This follows from Krappel's theorem and this description of activity here. So this is a theorem from my thesis, and then also from Bonin, Demier, and Noy. We proved it at almost the same time. And so they both are published contiguously in the journal, actually. It's kind of funny. But this tells you that this top polynomial just counts Dyck paths according to down steps, according to initial up steps and bounces. So this is one of the first examples where the top polynomial is really some combinatorial polynomial that you can describe exactly. Let me show you two things then. One thing that you might not remember is that our favorite matroid is the Catalan matroid C3. And so if you want the Catalan matroid C3, then if you want the top polynomial, all you have to do is draw all the paths. So here's one. There's another one. Another one. And then this one. And now you say, okay, x to the number of up steps, right? So you get x cubed and y to the number of bounces. This guy only bounces at the very end. Y plus x to the number of up steps initially, y to the number of bounces, 1 bounce, plus x to the number of initial up steps, y to the number of bounces, 2, plus x to the number of up steps, y to the number of bounces, 2, plus x to the number of initial up steps, y to the number of bounces. Hopefully, yeah, that matches. As it should match because these two matrices are isomorphic. So that gives you a nice way of computing this top polynomial. But now let me show you a corollary of this, which is that the number of paths with I initial up steps and j bounces equals the number of paths with j initial up steps and I bounces. It's a completely combinatorial theorem. How do you prove this theorem? What I'm saying is that the coefficient of x to the y to the j equals the coefficient of x to the j, y to the I. That this polynomial is invariant under changing x and y. But another thing that you might remember is that the dual of the Catalan matroid is the Catalan matroid. Because if the bases describe up steps, then the complements describe down steps. But if you just flip the picture around, the down steps just become up steps. So the Catalan matroid and its dual are isomorphic matroids, so they have the same top polynomial. And so therefore the top polynomial of Cn is the top polynomial of Cn star, but duality changes x and y. So there's the proof. Okay. And this is just, this was an accident. I proved this theorem, and then it just happens to give you this other theorem, and this wasn't known actually. So this was this nice enumerative consequence that just happens to fall out of the theory. The other consequence is that the number of paths with I initial up steps is equal to the number of paths with I bounces. Just follows from this. And that's not clear either. But it is. I mean, it's not clear a priori, but the proof is just take this and add over all j. And so this is nice, and it basically gives you some just purely combinatorial results out of the theory. There's an exercise that I want to give you guys to finish. Exercise. Number of paths with 2n steps that go either up or down and stay above the line x equals 0. That number is 2n choose n. So you want to count the paths that are kind of like Dyck paths because they're not allowed to cross the x-axis, but they are allowed to finish higher. Okay? And I'm telling you there's exactly 2n choose n of them. And the answer is so simple that it might make you think that this is a very simple question. But actually the easiest proof that I know is using this. So hint, this is the number of spanning sets. Of Cn. And we know how to compute spanning sets because the Tutte polynomial can be plugged in at 2, 1 and give you spanning sets. So that's your exercise for today. That's it.
I was astounded.